Okay, in this video we'll discuss the URMS one more time. Recall from a previous video that the root mean square velocity is equal to square root of 3RT over the molar mass. What that means is that if your temperature is constant, since we know that 3R is a constant, that means the velocity is going to be inversely proportional to square root of 1 over m. And let's take a look what that means graphically. How can we interpret over various different given samples of gases? So let's say you have two gases. You're plotting the molecular velocity. Since it's a velocity, probably the units will be in meter per second. And on the y-axis I have the number of molecules with indicated velocity, indicated velocity. And suppose I give you that I have two curves, maybe something like that, and I have another one which looks kind of like that. Both of these are measured at the same temperature. Maybe this is like 2000, maybe that one is a 1000. My question is, let's say my given two samples are oxygen and maybe hydrogen or helium. Let's go with helium just for a change. Now you know that helium has a molar mass of 4 grams per mole. Oxygen, being diatomic, will have a molar mass of 32 grams per mole. That means the average velocity of oxygen is going to be lesser as compared to that of helium, and one can say that at the same temperature, the number of molecules that will have this velocity of 1000 or so is going to be lesser, which is why you have such a narrow, such a thinned out graph. On the other hand, if you think about this curve, for the case of helium, since helium has a smaller mass, that means more fraction of molecules will have greater velocities. And that is the reason that this region has become much more flat, and you see that more and more number of molecules have that greater velocity. It is really imperative to realize that for any curve, be it oxygen or helium, whichever curve you're looking at, the distributions that you're getting from these Maxwell distribution curves, Maxwell distribution curves, is that while there might be some molecules which indeed are traveling with the URMS, the root mean square velocity, there is a possibility that there could be some particles that are traveling faster, and that's also possible that there will be some molecules which are going to travel slower than the root mean velocity. And so one can say that things like helium and hydrogen, the velocity distribution is a little bit shifted towards the higher velocities, and that is the reason that in the previous slide, the curves that I showed you, they looked a little bit broader because of the wide range of velocity. Now, you can even do another study based on variable temperature. So again, I'm going to plot the number of particles with the indicated velocity, and I'm going to plot that against the molecular velocity, so that units of that would be meters per second. And let's see what the plot will look like, perhaps at 273 Kelvin. As you increase the temperature, curve tends to flatten out. Maybe let's say that's 500 Kelvin, and then it flattens further out. Maybe that's 1000 Kelvin. That means as I am increasing the temperature, the curve tends to flatten out. And the reason for that is because as the temperature of the gas sample increases, the velocity distribution increases. So more and more particles go through that minimum threshold velocity. They acquire that velocity, and hence your curve will become less sharply peaked, or in other words, it tends to become broader. That means the population density having velocities greater or close to around the URMS, or maybe even higher, that is going to increase. So just out of curiosity, I'm a little curious if we have, let's say I give you maybe 3 balloons, and I put 3, 4, and 5. I have 5 particles of gases in one. I have another one. It's just that the particles are a little bit massive in the second case. Let's call this one A, let's call this one B, and I'm going to give you another C where I have a greater population density. And if somebody asks you which of these samples of an ideal gas has the greatest pressure, hopefully you can see that if the 3 are maintained at the same temperature, then hopefully you can see that the number of particles in C is maximum. This one has maximum number of particles, and so the population density of the particles is highest, which means the collisions are going to be highest in this case, leading to the greatest amount of pressure in case of C. While in case of B, you do see that the particles are massive, but then their velocity is going to slow down, and so the kinetic energies of the two is going to be similar because you have same number of particles and you're maintaining that at the same temperature. So the average kinetic energy is going to be exactly the same. I want to now discuss with you the Graham's law of effusion. This is based on the rate at which molecules move, and so hopefully you can see that that rate is proportional to the root mean square velocity. So it will be a measure of the root mean square velocity, and since that is 3RT over the molar mass square root of that, one might be able to say that if we are studying relative rates of effusion or diffusion between two gases, so let's say I have two gases that I would be able to say rate 1 for the first gas, and I would be able to write a similar equation, rate 2 proportional to the URMS of that gas, or MS of that gas, and given as 3RT over M2, one might be able to say that the relative rate, rate 1 over rate 2, will be equal to the square root of 3RT over M1 whole divided by 3RT over M2. 3RT and 3RT will cancel off, and you might be able to say that square root of the molar mass, I should write this as molar mass, M2 over M1 is going to give you the relative rate, rate 1 over rate 2. In other words, one can say that heavier is a gas. Let's say the gas is heavy, it's going to travel, it's going to move around much slower than a light gas. So we're going to see an application of this in the form of a question, and the question here is, under the same conditions an unknown gas diffuses 0.644 times as fast as SF6. This question is given in the PowerPoint on slide number 40. So you've been given that there is some gas, some unknown, and the rate at which it diffuses is 0.644 times as fast as sulfur hexafluoride, the molar mass of which is 146 grams per mole. What is the identity of the unknown gas if it is also a hexafluoride? So let's assume it's something like, MF6 perhaps. Okay, so this is my unknown. Now, you're given that if SF6 moves at, let's say, some x velocity, then the MF6 is going to move at 0.644 times that x. That means that if, let's say, SF6 is going at a rate of 10 meters per second, then MF6 is going to go at 6.44. So you can perhaps envision that the MF6 is perhaps it's a heavier gas, heavier than the sulfur hexafluoride. But anyway, what you have to do here is you have to apply the Graham's law of effusion, according to which rate 1 divided by rate 2 is square root of molar mass 2 divided by molar mass 1. Now realize in this case it really doesn't matter which one you want to put as 1 and which one you want to put as 2. I'm just going to put rate 1, let's say anything that contains 1, I'm going to say that belongs to SF6, and anything that shows up as 2, the subscript 2, I'm going to say that's my unknown. Okay. And so if rate is x, that means rate 2 will be 0.644 times x, and that will be equal to, M2 is what I'm seeking, M1 has been given as 146 in my question. X and x will cancel off, and you will need to take the square of both sides of this equation. So let's see what that will look like. So 1 over 0.644 square of that is going to be equal to M2 over 146. What does that imply? Okay, so 1 divided by 0.644 will give you 1.5527, and you'll have to take a square of that, and that will be equal to M2 divided by 146. So from here, turns out that M2 will come out to be somewhere close to 352, 351.5 is what I'm seeing. So M2 is going to be equal to 352, let's say approximately. It came out to be 351.5 grams per mole. Now the question says further that it is MF6, it's a hexafluoride. Each fluorine is 19 grams per mole. If you have 6 of those, that means you have 114 grams per mole. What does that mean? That means that the molar mass of M plus the 6 fluorine atoms together make up this 352. So if I subtract the 114 due to the fluorines from the 352, don't you think I would get the mass of the unknown metal? So let's give that a shot. 352 minus 114, that gives me 238 grams per mole. And if I read on the periodic table for the masses, 238 is clearly giving me for uranium. So that means UF6 is one possible answer for this particular question. You might question what is the difference between diffusion and effusion. Diffusion and effusion. And while the basic principle is the same, diffusion as a process depends, it relies pretty much on collision of gas molecules collision of gas molecules through space. So through space. So you can perhaps see that this is going to be a slow process. A great example of this would be, let's say you're baking a cake, okay? So you are sitting in front of, I don't know, maybe your television or something, and here's where your kitchen is, okay? And you set up the cake to bake, and it takes several minutes before you're able to get the smell of the cake. Why? Because as the cake rises and the vanilla vaporizes off, you actually see collision of vanilla here, here, maybe at the back, then forward. So it's a zigzag motion, it's a random motion, which ultimately, eventually, gets to your nose and you're able to smell it. As compared to that, if you look at effusion, effusion also relies on collision of gas molecules, but they have to pass through a small hole, a pinhole. There is no pinhole that is present in case of diffusion. So each molecule has to pass through a pinhole. So one would be able to perhaps envision that effusion as a process is even slower than diffusion. And so a classic example for that would be if you have, let's say, microwavable dinners which are covered with cellophane membrane, and now you are warming it up in the microwave and you are able to get the smell of that. In that case, the herbs, they will rise, leave the surface of the cellophane, and then they will have to go through a diffusion, and you will be able to get the smell of that. So effusion, realize it's a very slow process. The success of that does depend on the slit or the pinhole that we are referring to, but it does have to involve a small pinhole through which the molecules have to move. Whereas diffusion as a process relies solely on the collision of gas molecules through space, and hence you can consider that to be a slow molecule as well.